Okay, welcome to ELE 112. This is the series parallel RL and RC homework lecture helper. It covers series parallel RL and RC circuits. So let's get going. I'm going to extend a few of these problems with a few extra things to help you out. But take a look at that circuit on the top left. It consists of inductors and resistors. And you'll see that I have gone ahead and circled the very first circuit up at the top. And I think and I hope that all of you identify that circuit as parallel. So first thing I'm going to do is I'm going to compress away from the battery. I can't stress this long enough and often enough. You want to compress away from the battery, get to the right of the circuit, and start compressing. So when you calculate ZR1L2 using product over sum here, you end up with 1.788 at an angle of what appears to be 26.565 k ohms. That is not negative, that is positive. The circuit then moves down and breaks down into what I call a simple series circuit, where once again I've gone to the box technique and I've made each of the resistors, each of the inductors an impedance, and I'm using just the simple series circuit like I did in chapter 5 and 6 with resistors. So I'm treating the capacitors, the inductors, just like I did the resistors, rather than use all those Mickey Mouse formulas in your book. When you add all of this together, you end up at 3.22 k ohms at an angle of 60.255. What do we usually do with chapter 5, chapter 6 problems? Once we get impedance, we move down and we calculate the total current. It's a natural. So from impedance total, which, if you can't get ZT, you're stuck. You're in a hole. The total current becomes 10 at angle 0. Why are we using angle 0? Every power supply gets angle 0 tucked in the back. Every power supply. VT over ZT produces the impedance shown 3.1 or the current shown 3.101 at minus 60.255 milliamps. So that's our total current. I want you to notice that this inductor L1, it's in series with the battery, so it sees IT going through it. How easy would it be to calculate that voltage now that you have IT and X sub L1? Well, maybe on the next page we'll do it. So here's my question to you. Who dominates this circuit? If I was starting this problem at the top, I couldn't answer that question without doing a little bit of analysis in my head. But by the time you calculate ZT right here, you can tell a lot by a series parallel circuit by just looking at the phase angle. That 60 degrees says that the inductor dominates this circuit. On page 2, we go back. Here's the original circuit just for your convenience, being shown up there with the new value shown here, just in case you need it while you're working. Now, if you take a look at the original circuit that's here that we broke down by combining the parallel section, you'll notice that that's a series circuit. So since we know the voltage at L1, since we know the voltage at L1 can be computed, we go ahead and do that right here using nothing but Ohm's law. Realize that you could have used voltage divider here in this circuit because it's nothing more than a simple series circuit. There we go. Maybe now we won't get all the circuit moving. So after we compute the voltage at L1 to be 6.201 volts, we can then take a look at L2R1 and say, hey, the voltage of R1 and L2 being in parallel, they have to be the same. So if I was able to, in green here, if I was able to compute this voltage, I would actually have the voltage of the two components. True? So I go about that right here. I take the total current, I multiply it by the value that I got up here on page 1, and I get my voltage. Now, a good thing to do is to take the L1 inductor and resistor 1, for example, and check that you did something right. Use KVL to check that the sum of the voltages is equal to the power supply in that path. Now, you don't have to check it with the inductor and the inductor L1 and L2 because R1 and L2 are in parallel, right? So if you check one, you've checked both. And I went ahead and checked, and I see that I did a pretty good job here of making the calculations. Again, I will tell you that the phase angle of 0.0077 is essentially 0 degrees. In the third slide, or the third page, I break apart this parallel, and we do know the voltages at this point, which that allows us to find the currents. We could find it in one of two ways. It doesn't matter which way you work. We could use Ohm's law. We could use current divider here. You see, we know the current coming into this junction, IT. We've already solved for IT, so we could use current divider. Why don't you try that as a challenge? I'm going to use Ohm's law right now and just take the resistance of R1 and divide it into the voltage, which we already know what the parallel branch brings, and we come up with this current for IR1, and we use the same technique to find the current through the second inductor. Essentially, we've completed the whole problem. Now, it seems like a monstrous problem, but that's because I'm trying to teach it to you. I'm trying to show you lots of different things. I'm trying to give you options like which formula do you want to use to do the problem. And at the very end, I've added a bonus. I'm just going to draw the phase diagram of all the voltages in the circuit. Now, there are 3 parts, but 4 voltages. The battery counts as 10 at 0. And then we grab each of the voltages. Here's VR1 and VL2. They're combined together. Now, you guys make these phasor diagrams out to be something very difficult, but once you've got the right answers, you just follow the phase angle. This phase angle is just minus 33.690 degrees. Just slide down, draw a length that obviously needs to be less than 10. It needs to be 5.5, so about halfway. And then draw the voltage for the inductor in the first position, the 2K. Make it a little bit longer than 5, but shorter than 10. It's up at 29 degrees, so show that angle, and you're done.